All right, so we're going to look at the molecular orbitals of the simplest conjugated diene, so 1,3-butadiene. Okay, so first off, let's do this. So look at atomic orbitals. How many p orbitals are there in the conjugated butadiene? There are 4, right? So p orbital on each carbon, 1, 2, 3, and 4. So I'm going to write 4 p orbitals. Okay, so 4 atomic orbitals. And how many pi electrons are there? 4 as well. So one orbital got 1 electron. So I'm going to put 1, 2, 3, 4. All right. Now, when all these overlap, right, all 4 p orbitals overlap, you're going to get 4 new molecular orbitals. So how many atomic orbitals you get when they overlap? You're going to have the same number of orbitals. But right now we call molecular orbitals now. Okay. Now here's the shape or the structure of the molecular orbitals of that this diene. All right. So if you remember, like the constructive interference, all orbitals or electrons, they are on the same phase. So I can go like that, but up, 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 and up. They are line up perfectly. Okay. Now we go up to the higher energy level. So I'm going to flip 2 of them, and you're going to have 1 node. No, you might have a question, but hang on. We will get there. Why 1 node? What's going on? Over there. Go up. Go to up higher in one energy level. So right here we're gonna have 2 nodes, and then you can guess you got 3 nodes. Okay. So you may ask, how do I know how to draw the molecular orbitals? All right. So I'm going to make it simple here. You start with the lowest one. All of them are line up perfectly. They are all the same phase, right? So all up. When you go up higher energy level, next one is going to be 1 node, which means that the little destructive interference. So I'm going to move 2 on the right side or the left side, move down, and that's you get 1 node. Go up higher energy level, this is going to become 2 nodes. To do that, you're going to go up, down, down, and up. Okay. And to go to the next one, we need 3 nodes. You're going to go up, down, up, down. All right. And you try to make the shape of molecular orbitals symmetrical. That's control. How you draw the shape of it. All right. We'll practice some more later. So this one for butadiene. I got a couple more examples. Anyway, all right. So now for atomic orbitals, you get 4 molecular orbitals. Now for electrons, how would I put them in the molecular orbitals? Go with the excuse me, go with the lowest one. So we have 4, so 1, 2, and then before go up to the go up higher energy level 3 and 4. All right. Also, let's compare this to what you have in the textbook. Similar. Yeah, you can spend time looking at it. It's really similar there. All right, so we're gonna focus on here. So we're gonna use molecular orbitals to explain some property that we talked before. Okay. Number 1, if you remember the bond length, I said that this bond is shorter than the regular single bond. Here's why. Okay. This bond right here between C2 and C3 is formed right there. Right. Now, in the lowest energy orbitals, right, the lowest MO, there's a pi sigma bond and pi bond in here. Make sure you get what I just said. Now say one more time. In this MO of butadiene, the bond between C2 C3 got sigma bond and got pi bond. Okay, so have sigma and pi character. All right. But if you go up to a higher energy level, go up to 1 energy level, there's a node there. And a node is mean there's no electrons. So there's no pi electrons in here, just sigma. My point is the bond right here has both single bond and double bond character. Now I have both single bond and double bond character. The single bond is that long. Double bond, and you know double bond character. Double bond is shorter than single bond. This bond right here is a mixture between a single bond and double bond. That's why it's shorter than the regular single bond. Yep, and we can explain that. Okay. One more, the stabilization energy of 15 kilojoule per mole. Why do you get that? All right. If you see right here that excuse me. All right. The electrons in butadiene delocalize in 4 p orbitals, right? So 4 p orbital. That's why you see like all the continuous blob of electron density. Okay, and that actually makes the conjugated diene stable by 15 kilojoule per mole, compared to what? Compared to a regular alkene where 2 electrons delocalize in 2 p orbitals. This is 4. Electrons love space to travel. right? And that make electrons really stable. So 4 p orbitals versus 2 in p orbitals in on a regular alkene, isolated alkene, I mean. All right, so we're gonna practice on this together. So all you have to do, draw the molecular orbitals, fill up the electrons. We do this on the next video. Okay.